Now let's take a minute to look at this alpha cleavage example. There's something that I want you to recognize. Let's look at pentane 2-ol. Get my pen going. Pentane 2-ol. Okay. All right. So under electron ionization, one of these electrons, an electron is going to be lost, but we're going to show it on the oxygen, and we form the radical cation. Sorry. With a positive charge. So this is now our molecular ion. We won't see this molecular ion because this alpha cleavage is so favored that there'll be no parent molecular ion to see. So the alpha cleavage, this is our alpha carbon here. The radical ion is going to come down. We're going to use a single fishhook arrow to show that it's a single electron. And then we're going to have homolytic bond cleavage here. So one of these is going to go to this, and one is going to go here. So what we're going to end up with and I'm just showing our resonance stabilization. And along with that, we're going to have, and then the radical is going to remain on the CH3, CH2, CH2. That showed the this bond breaking, but it's equally possible that this bond would break. So there will be two fragments that come from this alpha cleavage. So I want to clean up a little bit here. So this oxonium ion carries a positive charge on the oxygen, and in the resonance structure, the positive charge is here on the carbon. Now, talking about the other bond to the alpha carbon breaking, if after ionization, so now we have our radical cation, we have this bond breaking, and the radical electron onto the methyl group, we end up with a different oxonium ion and a methyl radical. Now the pentane is C5H12O. So just using nominal weights in my head, the molecular mass is going to be 88. And then these fragments in this oxonium ion, we have CH3, CHOH. And that will give us our mass of 45. And then looking at this other fragment, we have the other alpha cleavage product. We have CH3, CH2 twice, CHOH, which should give us 73. So we're looking for a molecular ion of 88 and fragments at 73 and 45. Let's pull up the spectrum. And what we've got here is the mass spectrum, the EI mass spectrum of 2-pentanol. And we don't see a molecular ion peak at 88, but we do see 73 right here. And then 45 is our base peak. So this is the alpha cleavage product. So diagnostic for the alcohol. Now let's just briefly look at the other common fragment from alcohols, and that would be dehydration. It isn't necessary to be able to do all the electron pushing for the various fragments. Sometimes this will be shown because it's well understood. A lot of these reactions are gas phase radical reactions, and they are difficult to predict. After seeing enough of them, you can begin to rationalize how the electrons move, but it's not critical that you be able to draw all of the intermediates in a fragmentation. What you need to recognize are the stable radical ions that are formed and detected, and the loss of neutral molecules, because the loss in this case, when we have dehydration, we're going to have the loss of 18, and that loss of 18 is characteristic for a dehydration. Now, just as an example, I'm going to use hexane 3-ol or 3-hexanol. So the loss of water is going to result in H2O leaving and formation of a double bond. And this fragment will be detected, and the loss will be seen as 18, but there'll be no 18 peak because this is a neutral molecule. And our initial molecular weight was 102. So 102 minus the 18 is going to give us 84. I'm going to pull over the spectrum. And in this case, the 84 peak is just about 1% relative abundance, so not that strong a signal for hexane 3-ol. What we see is the most prominent peak is here at 59, and this is the alpha cleavage product. So see if you can get to the alpha cleavage product that gives you the M over Z 59 ion. It should be good practice. Now I just want to take a minute and go over the Greek naming system for compounds with carbonyls. The double bond to the oxygen is the carbonyl carbon, and then we're using Greek letters to name the carbons according to their distance from that carbonyl. So there will be typically, it'll go off in two directions. So alpha, beta, gamma, delta in this ketone. So the other functional groups are named relative to this. So here, beta hydroxy ketone, because the hydroxy is in the beta position. And here we have unsaturation between the alpha and beta carbon. So this is an alpha beta unsaturated ketone. This with the two carbonyls, the second carbonyl is beta to the first one, so that's a beta keto ester. One other thing to mention for ketones, you will see it going off in both directions. For aldehydes and esters, it's not able to go off in the other direction. But in this case, rather than having two alphas that you can't distinguish, it's typical to put prime marks on one set of the alpha. So it would be alpha prime, beta prime, and then alpha and beta. And then typically going to gamma is quite normal, delta, even epsilon, but I don't know that I've ever seen it go out beyond epsilon. It's too far removed from the ketone to be involved in chemistry with the ketone. But this gamma position is important for because of the ability of this position to allow a six-membered ring to be recognized. So 1, 2, 3, 4, 5, 6, that this atom is capable of interacting with the lone pairs on the oxygen, and there's a strong preference for six-membered rings, so often you will see chemistry at the gamma position when the carbonyl is present in the molecule. Now, amines will behave very much like the alcohols because of the unshared pair of electrons on nitrogen. The alpha cleavage reaction rearrangement is very common, and you should expect to see fragments corresponding to these cations. The loss of neutral ammonia, like the loss of water, is also possible. I don't know that that's a big pattern to observe in small molecules. A rearrangement that's important is the McLafferty rearrangement. Fred McLafferty was one of the people that pioneered electron ionization mass spectroscopy. In this rearrangement, the gamma position, so there are a couple of requirements that are necessary for the McLafferty rearrangement. You must have unbonded electrons, and you must have a hydrogen at the gamma position. So alpha, beta, gamma position, and you must have pi electrons. So in this case, you have homolytic cleavage between the alpha and beta position, and transfer of the proton joining the carbonyl for this fragment to leave as a charged ion that you will see in the mass spec. And then this fragment, pardon me, let me get a pen here. This fragment will leave as a neutral molecule and will be seen as a loss. So there are going to be characteristic losses, and you can find large tables if you're routinely analyzing mass spec for structure elucidation to help. But loss of a methyl radical would be loss of 15, ethyl 29, propyl, butyl, loss of water. In the McLafferty rearrangement, the value of X, the number lost, would correspond to that neutral fragment that's lost. Now, the availability of high-resolution mass spectrometers has really improved the power of mass spec, and also made it much easier to use mass spectrometry to solve structures. in a high-resolution mass spectrometer, the M/Z ratio can be measured up to 4 decimal places. What we've been looking at up until now, we're using nominal molecular weights. We're just counting protons and neutrons to come up with nominal molecular weights. But you recall that a proton, while we say it nominally has a mass of 1, and it has an actual mass of 1.0073 atomic mass units, and a neutron nominally also 1, but with a different mass when going out to 4 decimal places. Our atomic mass scale, we've established carbon as having 12.0000 AMUs, because that AMU scale is based on the carbon-12 isotope, and every other atom's mass is relative to this. So when we measure the mass to such a high precision, we can, well, let me I don't like this table too much. This table wraps around on itself, so to fit on the slide. What you see here is that carbon-12 has exactly 12.0000. We talked about this before. It's 98.9% abundance, or roughly 99 to 1 relative to carbon-13. Chlorine isotope, our 3 to 1 ratio in our chlorine isotope, our roughly 1 to 1 ratio in our bromine isotope. But determining mass to this level of precision means that only certain atoms can sum to give us this value. And with computers, we can mathematically predict masses. So in this example, we have cyclohexane with a nominal molecular weight of 84 and an exact mass of 84.0573. And cyclopentanone with the same nominal molecular mass, the exact mass is 84.0939. And this is based on the mass of the isotopes and their relative abundance. So with high-resolution mass spec, we can distinguish these two molecules, and we could not do that with standard or what now you might call low-resolution mass spec, but had been the norm until high-res mass spec was developed.